Welcome to this video about non-destructive evaluation, NDE, technologies for concrete. After watching this video, you will understand the importance of conducting NDE tests and the procedures for doing so. To obtain the mechanical properties and durability of a structure, we normally require coring of an in situ structure. And this is why these tests are known as destructive tests. Compared to these tests, NDE tests do not disturb the concrete structure or only do so minimally. So a large area can be studied without extensive coring of samples. In this video, we introduce 5 common NDE tests: electromagnetic, ultrasonic pulse velocity (UPV), infrared thermography, half cell potential, and the surface hardness test. For the first 3 NDE technologies, electromagnetic, UPV, and infrared thermography, thanks to the scientists like Michael Faraday, James Clerk Maxwell, Ludwig Edward Boltzmann, and many others, founded the theories of electromagnetism, sonar, and heat transfer in the late 18th century. During the 2 world wars and other wars, scientists and engineers invented technologies based on these theories and applied these technologies in the battlefield. Later, until about the 1970s, many of these technologies became available for civilian use, such as aviation, geophysics, medical imaging, and also civil engineering. The first test we introduce in electromagnetic test is ground penetrating radar. A radar antenna emits high frequency electromagnetic waves in the microwave bandwidth. Commercial radar systems for concrete applications range from 500 MHz to 3 GHz. Radar detects the reflected signals. During the Second World War, radar was used in coastal defense and on warships to locate the enemy's air fighters and bombers, so that air fighters could tackle the enemy at the right place and at the right time. After the war, scientists probed the radar antenna from the sky to the ground and directed the antenna from ground-based to moving around. So now, civil engineers follow these footsteps to study what is inside concrete and other subsurface structures. A common radar system is comprised of 2 antennae, a transmitting antenna and a receiving antenna inside the same shielded box. When an antenna moves, the transmitting antenna sends out a wide-band electromagnetic pulse in the material. When the pulse encounters an object with an electrical property different from that of concrete, a reflection comes back and the receiving antenna records the reflected signals. The object can be a steel bar, void, or interface between concrete and soil. Now we perform a survey of a concrete surface. We normally carry out radar transverses to make a grid in both X and Y directions. Spacing of this grid should be at least half of the bar spacing. For example, the grid size should be 100 mm if the spacing of the steel bars is 200 mm. Outside the shelf of the antenna box, there is a wheel odometer that triggers the antenna to collect reflections when the antenna moves on the concrete surface. Compiling these waveforms reveals the concrete structure as a two-dimensional radiogram. In the radiogram, we can locate the position and depth of the steel bars by recognizing the hyperbolic reflections. After processing of the signal, slice views at different depths can be unfolded, and a three-dimensional view can also be obtained. Another simple electromagnetic method to locate steel bars in concrete is by using cover meter. A cover meter search head generates a magnetic field. When a metal lies within this field, eddy currents are produced and induce a strong magnetic field in opposite directions. Position, concrete cover, and alignment of steel bars can then be estimated. There are a few steps to carry out the measurement. A. Prior to the test, input the bar size according to the drawing to estimate the concrete cover. If you don't have the bar size, input 16 mm as the standard value. B. Traverse the search head across the concrete. Observe when you see the reading of the energy bar reaches a maximum, and hear the bip bip sound. The energy bar indicates levels of disturbance due to the opposing electromagnetic field. C. Stop in this position and rotate the search head until a position of maximum disturbance is indicated. D. Read the indicated concrete cover if the bar size is known. E. In this position, the alignment of the steel bar is expected to fall in the plane of the center line through the poles of the search head. F. Mark this position on the concrete. Repeat this measurement at least 3 times in different positions to confirm the alignment. G. When you see that the reading of the energy bar reaches a minimum or a moderate value, and hear a much weaker beep beep sound, it implies that there is no embedded metallic object along the poles of the search head. Note also that if the bar size is not known, then the determined concrete cover's value is not accurate, but we can still determine the position and alignment. Failure of the test and loss of accuracy are due to factors affecting the magnetic field. When readings could not be understood, the signals are possibly interfered by densely spaced steel bars or other metallic objects. In such case, the more sophisticated radar method may be used. The second NDE test is ultrasonic pulse velocity, UPV test. Ultrasound is generated by exciting the piezoelectric transducer by a high voltage. Its frequency is beyond human hearing ability and is beyond 20 kHz. In this video, we will only focus on the compression wave, which travels in the same direction of wave travel. Other forms of ultrasonic wave, like shear wave and surface wave, will not be covered in this video. We cannot hear ultrasound, but imagine how water responds when you drop an aggregate into a pool of still water. The principles are the same. Similar to radar, an ultrasonic transducer sends out a pulse and receives the reflections from an object. Different to radar, the ultrasonic pulse is a mechanical wave, while a radar pulse is an electromagnetic wave. During the war, submarines were used to attack the enemy's fleet and supply vessels. The Navy therefore employed ultrasonic devices to locate the submarines accurately before launching torpedoes. Today, scientists have modified these devices to study concrete. With one transducer on one side and the other on the other side, ultrasound travels the shortest path in concrete. In general, ultrasound in good concrete normally travels faster than 4,000 meters per second. To carry out the test, first we measure the physical distance on the surface of the concrete. Second, place couplant on the sensors. Calibrate the probe using a steel tube with known travel time to make sure that the system works properly. Third, place couplant on the sensors and probe it to the concrete surface, one on either side. The couplant ensures a good wave transmission inside the. Fourth, start the measurement and record the travel time and waveform until it becomes stable. And last, calculate the UPV by dividing the path length by the travel time. With high density and modulus of elasticity yields a much faster UPV. When concrete contains large void or honeycomb because of inadequate compaction or other reasons, it slows down the UPV because the wave is diffracted and travels a longer path. So by mapping distribution of UPV over a concrete wall or slab, we are able to estimate possible position of void and honeycomb. Note also you should avoid UPV measurements close to steel bars. We locate steel bars by using GPR or cover meter. The third NDE test is infrared thermography. This technology can be understood as an array of non-contact thermocouples remote from the targets. It measures the temperature distribution over a surface in a composite material system, like tiles, or fiber reinforced polymer installed on concrete structures. After heating up the surface, we measure the decay of temperature to differentiate the places with good and poor bonding. The places with good bonding dissipate heat energy much faster than those with debond. Those hotter regions mean possible to bond. Another example is to track the heat emitted by jet engines of an air fighter, so that its position is located and attacked. Today, an important application of this technology in civil engineering is to study tile debond on wall envelope. There are 5 considerations which must be observed before and during the test. First, before carrying out the test, you require a minimum of 3 hours of direct sunshine on the surface to ensure that adequate heat energy is absorbed. Second, always compare the temperature distribution over the same exposed surface. Different exposed surfaces trap different amounts of heat energy because of the angle of exposure to the sun. Third, carefully observe the areas that are or have been shaded by barriers, such as adjacent structures and trees. Areas adjacent to barriers may become too hot due to either reflected heat or trapped hot air. Fourth, do not carry out the test when the wind velocity exceeds 30 miles per hour because convection blurs the heat transfer effect between good and bad bonding. Last, the temperature difference between good bonding and the debonded area should be at least 0.5 Celsius degree. The 4th NDE test is a half-cell potential test. This test method estimates the electrical corrosion potential of uncoated reinforcing steel in field and laboratory concrete. It predicts the probability of corrosion of the reinforcing steel in concrete. In this test, the circuit is connected to a full cell comprised of a reference electrode and a reinforced concrete. The reference electrode is a half cell with copper sulfate solution, and the reinforced concrete is the other half cell. There are 2 steps to carry out the test. The first step is preparation. The second step is measurement and data plotting. The first step is preparation. A. Scrape the barb before connecting the steel to the voltmeter. The purpose is to ensure a low electrical resistance connection. B. Make sure that copper sulfate solution is full at all times. C. Connect the anode of the voltmeter to the steel by means of a clamp. D. Connect the cathode of the voltmeter to the reference electrode. E. Pre-wet the concrete surface with fresh water. The second step is measurement and plotting. F. Design a grid of measurement. G. Place the reference electrode probe at the cross-section of the designed grid. H. Record the reading until it stabilizes. Repeat the measurement at the cross-section of the designed grid. I. Last, Plot the equipotential contour map to illustrate the voltage. If potentials over an area are more positive than -200 millivolts, the probability of corrosion is less than 10%. If the value is between -200 and -350 millivolts, the probability of corrosion is uncertain. If potentials are more negative than -350 millivolts, the probability of corrosion is more than 90%. It is important to note that this method indicates the probability of corrosion only, but not the rate of corrosion or its magnitude. If these parameters are of interest, you can refer to the polarization resistance method. The last NDE test is the surface hardness test. This test method determines the rebound number and predicts the surface hardness of hardened concrete by a spring-driven rebound hammer. This method assesses the in situ uniformity of concrete, delineates good quality concrete from poor quality, and estimates in-place strength. There are two steps to carry out the test. The first step is preparation, and the second step is measurement. The first step is preparation. A. Concrete elements to be tested shall be at least 100 mm thick and 150 mm in diameter. B. Grind heavily textured or soft surfaces, or surfaces with loose mortar until they become smooth. C. Remove any water present on the surface of the concrete. D. Ensure that no two impact points are closer than 25 mm and none is within 25 mm of an edge. The second step is measurement. E. Hold the hammer firmly in a position that allows the plunger to impact perpendicularly to the tested surface. F. Gradually increase the pressure on the plunger until the hammer impacts. G. After impact, maintain pressure on the instrument and depress the button on the side of the instrument to lock the plunger in its retracted position. H. Remove the hammer. Record the rebound number and use a minimum of 9 readings to obtain a reliable estimate of the rebound number for a test area. I. Record the position and orientation of the hammer for each set of readings. J. Examine the impression made on the surface after impact, and if the impact crushes or breaks through a near-surface airfoil, disregard the reading and take another reading. Concrete strength can be estimated by converting the rebound number through a conversion chart provided by the manufacturer. This conversion depends on the top-down, horizontal or bottom-up directions of the rebound hammer striking the concrete. A larger rebound number means a stronger surface hardness. However, these relationships may not fully consider in situ factors such as moisture content, type of finishing, and depth of carbonation. So far, we have discussed the significance of the NDE test and have shown the steps for conducting a proper NDE test. This test is used extensively all over the world, and its procedures are standardized in the American Standard of Testing Materials, the British Standards, and the Hong Kong Test Standard. Again, there are two main advantages of the test. First, all are non-destructive or minimally destructive to the concrete structure. Second, it enables a condition survey of a large-scale structure without the limitations of destructive sampling using cores. It has to be stated that NDE does not replace destructive tests, but rather works together with them. This is because NDE does not directly give the mechanical and durability parameters. For example, ultrasonic pulse velocity is related to, but does not directly indicate, compressive strength. So inversion from NDE to mechanical and durability properties is required. Inversion is subject to the types of sensors, signal processing techniques, and material properties. Formulation of these inversion methodologies is still a subject of research at the moment. By watching this short video, we hope you have been able to understand two main points: the procedures and the underlying principles of the NDE test for concrete, and the importance of the NDE test. So next time you are watching a war movie and are amazed by the technologies above water, underwater and on land, will you have more story to tell?